On July 1, 2025, a telescope in Rio Hurtado, Chile, captured something extraordinary, a fast-moving blur piercing through the Sagittarius constellation. At first, it was just another dot in the sky. But then came the orbit, hyperbolic. The speed, 58 km west, and the verdict, interstellar. Now officially named 3I, this is not from here. It's only the third object ever detected from beyond our solar system, after Oumuamua in 2017 and Borisov in 2019. But unlike them, this one is active, enormous, and heading straight through our planetary neighborhood. And while it poses no threat, it brings with it the unknown, discovery in the galactic glow. On the quiet night of July 1, 2025, at the Atlas Telescope Station in Rio Hurtado, Chile, astronomers captured a faint but fast-moving object sweeping through the dense star field of the Sagittarius constellation. Initially tagged as A1PL3Z, the object was notable not just for its brightness, but for its direction. It was inbound from deep space, coming in fast and at an angle not typical of solar system objects. Atlas, part of NASA's Asteroid Terrestrial Impact Last Alert system, logs thousands of nightly sky scans, but this one immediately stood out. Soon, scientists at the Minor Planet Center, MPC in Cambridge, Massachusetts, began compiling its early movement data. What startled them was how far back it had already been tracked. Observations from June 14, 2025 were identified in Atlas archives and also from the Zwicky Transient Facility in California. These pre-discovery sightings extended its observational arc, allowing for a far more precise orbital calculation. The MPC issued an electronic circular. The object wasn't native to our solar system. The data revealed a hyperbolic path, indicating the object had come from interstellar space. It was not gravitationally bound to the Sun, something only two known objects had done before, one Oumuamua in 2017 and 2I Borisov in 2019. This marked it as 3I Atlas, the third confirmed interstellar visitor ever observed. The excitement was immediate. The astronomy community buzzed with urgency, rerunning orbital simulations and sharing early observations across networks. But what exactly was this thing? At first, it wasn't clear if it was a rocky asteroid or an icy comet. Its brightness fluctuated slightly, but no coma or tail was visible in the earliest images. Still, the discovery was momentous. Something had pierced the edge of our solar system again, and this time we were watching it arrive from the very beginning. As the excitement spread, attention turned to a single question. What was this object made of? And where exactly did it come from? Astronomers dug deeper, analyzing not just its motion but its behavior. Because 3I Atlas was still inbound, it presented a rare opportunity, the chance to watch an interstellar visitor before it passed perihelion. And that's when things got even more interesting. What truly set 3I Atlas apart was its orbit. Most comets and asteroids follow elliptical paths bound to the Sun. But when astronomers ran the numbers, they found this object had an eccentricity of approximately 6.1, a value far exceeding the threshold of 1.0 for hyperbolic motion. That meant one thing. This object was not from around here. Its trajectory suggested it had come from far outside the gravitational grip of the Sun, hurtling in from the dark, empty reaches of interstellar space. Not only was its orbit steep, but it was also retrograde, traveling in the opposite direction of the planet's movement around the Sun. With an inclination of just 5 degrees to the ecliptic, it was slicing clean through the plane of our solar system like a blade from the galactic night. Its trajectory was heliocentric, yes, but not bound. Once it swung past the Sun, it would be on its way out, never to return. The object's incoming speed was another red flag. It was clocked at approximately 58 km/s as it approached, and was expected to reach up to 68 km/s near perihelion, making it the fastest interstellar comet ever observed. By comparison, Oumuamua entered at approximately 26 km/s and Borisov at approximately 32 km/s. 3I Atlas was on another level entirely. The speed, the angle, the orbit, it all pointed to a distant, ancient origin. Given its velocity and path, some models now suggest it originated from the galactic thick disk, a region populated by old metal-poor stars. If true, this could make the object between 7 and 11 billion years old, a true fossil from another star system, flung our way by some long-ago gravitational nudge. For scientists, It was like receiving a message in a bottle, one thrown across the Milky Way. Once its trajectory confirmed its interstellar origin, the next step was to figure out what it was. Was it active? Was it made of ice, like a typical comet? Or was it dense and dry, more like Oumuamua? As telescopes across the globe and in orbit pivoted toward the object, a new picture began to form. The early images were inconclusive, showing no clear signs of activity. But as July 2025 wore on, astronomers began seeing a faint halo emerge around 3I Atlas. On July 21st, the Hubble Space Telescope captured high-resolution images revealing a coma, the fuzzy cloud of dust and gas that forms when sunlight vaporizes surface ices. This confirmed its identity. It wasn't just a rock. It was a comet. With that, the object received a new name, C2025N13, Atlas. Soon after, a subtle tail became visible, stretching just a few arc-seconds in early exposures. While it was far less dramatic than Borisov's long gas trails, it was unmistakable. This tail pointed away from the sun, composed of carbon monoxide, carbonyl sulfide, OCS, and fine dust. Observatories worldwide began coordinating observations. The James Webb Space Telescope Gemini North and the Very Large Telescope joined in. The comet was no longer silent. It was speaking in light. JWST's NIR-SPEC and MARI instruments picked up CO2-rich emissions, as well as signatures of H2O, OCS, and carbon dust. The gas ratios were intriguing. The CO2-H2O ratio was higher than in typical solar system comets. Meanwhile, dust loss rates were measured at 6 to 60 kilon per second, modest but consistent with solar heating at 2 to 3 astronomical units. These values told scientists that 3I Atlas was warming, active, and rich in volatiles, but more subtly than Borisov. This activity also solved another puzzle. The object's brightness was increasing faster than expected. Now reaching magnitude 11.9 by August 2025, it was officially the brightest interstellar object ever observed. From its light curve, astronomers estimated a rotation period of around 29 hours. Its surface reflectance was slightly redder than the Sun, just like its interstellar predecessors. It had a story to tell. And now we had the instruments to listen. By late July 2025, 3I Atlas was putting on a subtle but measurable show. Observers noted that it was significantly brighter than either Oumuamua or Borisov at similar distances. As it drew closer to the Sun, its visual magnitude surged, going from approximately 20 in May to approximately 11.9 by August. That might not sound dazzling to the unaided eye, but for astronomers it was a beacon. This was now officially the brightest interstellar object ever recorded. The brightness wasn't just due to sunlight reflecting off its surface. It was enhanced by outgassing, the release of gas and dust from the comet's nucleus. This created a halo that reflected more light. The Las Cumbres telescopes, specifically the 0.36 Emmet pair in Hawaii, were used to monitor fluctuations in brightness across several nights. The goal was to detect a rotational light curve and determine whether the object was tumbling or spinning. Spectral analysis also showed that the comet was redder than the Sun, in line with previous interstellar objects. The red tint could be due to long-term radiation exposure in deep space forming complex hydrocarbons on the surface, a sort of organic sunburn. Yet unlike Oumuamua, this object had a distinct coma and tail, confirming active chemistry rather than a passive rocky exterior. The brightness, the chemical cocktail, the size, everything pointed to 3I Atlas being something unique. But what truly fascinated scientists wasn't just what it looked like. It was where it had come from. To decode that, they needed to reverse time, simulate paths, and ask what ancient force had hurled this icy messenger toward us. Its velocity held the key. At approximately 58 kilometers, 3I Atlas moved like a relic of the Milky Way. Older stars and the bodies orbiting them tend to move faster due to dynamical heating over billions of years. By applying models that link stellar velocity to age, estimates suggested 3I Atlas could be between 3 and 11 billion years old. That would make it older than our solar system, which formed around 4.6 billion years ago. If true, this comet was forged in a time before Earth existed, likely in the icy fringes of a red dwarf system, where carbon-rich environments allowed hypervolatiles like CO and OCS to freeze and embed in forming comets. Ejected by planetary interactions or passing stars, It had wandered the interstellar medium for eons before colliding with our gravitational sphere. Borisov had resembled our solar comets. Oumuamua had challenged our definitions. But 3I Atlas, massive, active, and ancient, was something in between. A reminder that not all interstellar objects fit into neat categories. Understanding its origin only deepened the mystery. If these kinds of objects are out there wandering silently for billions of years, how many pass unnoticed? How many stories have already slipped by in the dark? The only way to answer that was to ask a harder question. How rare are these encounters really?